So on the one hand, we have linear transformations, and on the other hand, we have matrices. There's sort of this interplay between them because we thought about linear transformations to define the matrix operations, although I called them linear vector functions at the time. And on the other hand, we've seen that any matrix determines a linear transformation, right? Because if we have an m by m matrix A, then define a function from Rn to Rm that's given just by multiplication on the left by A. Then we can check the characteristic property of linear transformations in a really straightforward way. So suppose we have this combination R1v1 plus R2v2. Here v1 and v2 are in Rn, and R1 and R2 are scalars. Well, if this is our definition of this transformation T, then applying the transformation T is just multiplying on the left by A. So A times R1v1 plus R2v2. You have to be a little careful looking at this kind of expression because this operation is applying a function, and this operation is matrix multiplication. So I know they look the same. They're both just some letter written next to a set of parentheses, but they're different things, right? This one is applying a function, that one is matrix multiplication. But now that we have matrix multiplication here, we can use all the algebraic properties of matrix multiplication. We can distribute the A across the sum, and then we can move the scalar multiple to the left of the matrix multiplication, and that gives us R times AV1, R1 AV1 plus R2 A times V2. But A times V1, that's exactly the formula for T. So this is T applied to V1. And then R2 times A times V2, that's T times, or T applied to V2. And so we see that this linear transformation that's just multiplication on the left by A is a linear transformation. So multiplication, if you have any matrix at all, multiplication on the left by that matrix is a linear transformation. So every matrix gives us a linear transformation. Well, does that go the other way? I mean, every matrix gives us a linear transformation. Is it possible to come up with a matrix for any linear transformation? So if we have a transformation to get a matrix that defines that linear transformation. In particular, what I mean is if we're starting with a linear transformation from Rn to Rm, can we find a matrix A, which will have to be m by n, so that the formula for the linear transformation is actually just multiplication by A? Well, let's think about how that would work. I mean, a linear transformation is we've seen that all we really need to know to define a linear transformation is we need to know what that transformation does to a basis. So maybe we should think about a nice basis for Rn. And the nicest basis for Rn is the so-called standard basis, which usually we call E1 through En. And these are just the vectors that have a 0 everywhere except in one spot. So E1 has a 1 in the first spot, En has a 1 in the last spot, and so on. E2 has a 1 in the second spot, E3 has a 1 in the third spot, and so on. There are n of these vectors, and they're obviously linearly independent, so these do form a basis for Rn. So because a linear transformation is determined by its values on a basis, we know that T is determined by its values on this basis. So T of E1, T of E2, and so on, all the way down to T of En. So knowing these vectors is enough to determine what linear transformation we're talking about. Well, if we're trying to find a matrix A that mimics or produces this linear transformation, we should see what A does, right? We're hoping that A provides a formula for T by matrix multiplication. We know what T does to these standard basis vectors. So let's see what A does to these standard basis vectors. So just to have a little notation for A, let's say that the columns of A are A1 through AN. Okay, so let's see what A does when we multiply it by E1. Well, remember, E1 is just the vector that has a 1 only in the first entry and then zeros elsewhere. So if we sort of tip it sideways and do our matrix multiplication, right, the only place where we get anything but 0 is when we do these multiplications down the first column. And so right, this 1 just sort of picks up everything in the first column. And so A times E1 is just the first column of A. What about A times E2? Well, we can do the same thing. Have a 0 and then a 1 and then nothing but zeros afterwards. You can see that this is just going to pick up the second column. So A times E2 is the second column of A, A2. And so on, all the way down to the last one, A times En. So En is the standard basis vector that's all zeros except there's a 1 in the last entry. And then when you do this matrix multiplication, that 1 just picks up the last column. So A times En is An. So comparing these, right, we're hoping to come up with a matrix so that multiplying on the left by A does the same thing as applying T. Well, these outputs, these A's, these columns from A, these are the outputs that multiplication by A produces. These products, T applied to E1 up to T applied to En, these are the outputs that the linear transformation actually produces. So these are what we want. These are what we would get from multiplication by A. So we should just insist that these columns are these vectors. And that should do the job. So what we're saying here is we've found A. A is the matrix whose first column is T applied to the first standard basis vector. The second column is T applied to the second standard basis vector, and so on, down to T applied to the nth standard basis vector. And that should do the trick, right? Because now if we take a standard basis vector and multiply on the left by A, we get T of E1, right? Or T of EI. And this is for I from 1 up to n. So what this is saying is now multiplication on the left by our matrix here agrees with the linear transformation for this basis. But remember, a basis determines the linear transformation, so that means these have to be the same linear transformation since they agree on a basis. If they agree on a basis, they'll agree on everything. So this gives us a recipe for turning a linear transformation into multiplication by a matrix. We already knew that every matrix gives you a linear transformation, and now we can go the other way. So what we're finding is that linear transformations and matrices have this correspondence between them. If you have a linear transformation, you can produce a matrix so that multiplication by that matrix is that linear transformation. And if you have a matrix, it gives you a linear transformation by doing multiplication on the left by that matrix. So there's this firm correspondence between linear transformation and matrices. Do keep in mind that linear transformations and matrices aren't exactly the same thing. A matrix is just a big rectangle of numbers, and a linear transformation is a function from Rn to Rm. it's only when you write down this formula that a vector gets sent to A times V. It's when you write down this formula that a matrix determines a linear transformation. Okay, so let's use this idea to come up with a matrix for a linear transformation. Let's find a matrix for this linear transformation. You can see this linear transformation T is determined on the standard basis for R2. Right, here's E1 in R2, and here's E2 in R2. So what we've said is the matrix for this transformation is just the matrix whose first column is T of E1, and whose second column is T of E2. And then we're done, because we only have two basis vectors. So that's 2, minus 3, 1, 4, 4, minus 3. You can see, really, we're just taking these vectors and popping them into a matrix as columns. So you can see that this way of generating a matrix for a linear transformation is actually pretty straightforward if what you know about the linear transformation is the linear transformation on a standard basis. Let's look at one more example. Let's find a matrix for this linear transformation. So there are a couple ways to go about this. We know that if we can figure out what this linear transformation does to a basis, then we can just throw all those vectors into a matrix as columns. So one way to do this, let me do it over here. One way to do this is figure out what is T of 1, 0, 0. And for this, we can just use the formula for it over here. Looks like it's going to be 1, 1. And then figure out what is T of 0, 1, 0. And again, use the formula. Now this 1 is in the B position, so 0 and 1. And then work out what is T of 0, 0, 1. This is E3, the last standard basis vector for R3. Right, now this 1 is in the C position, so minus 2 and minus 3. And now that we know what the transformation does to the standard basis vectors, we can write down the matrix for this linear transformation. It's 1, 1, 0, 1, minus 2, minus 3. And that's it. We're done. Another way that we could have done this is, right, we could have, and this way, I think maybe it's a little more writing, but it kind of displays how T is really just multiplication by a matrix in a little more visceral way. So T of ABC is really T of A times 1, 0, 0 plus B of 0, 1, 0 plus C of 0, 0, 1, right? We can pull apart this column vector. And since T is a linear transformation, we get A T of 1, 0, 0 plus B T of 0, 1, 0 plus C of 0, 0, 1. Sorry, T of C times T of 0, 0, 1. Okay, well, using the formula, you can see that this is A of 1, 1 plus B of 0, 1 plus C times, sorry, I said A of and B of, A times 1, 1, B times 0, 1, C times minus 2, minus 3. And now comparing this expression and this expression, you can see that T of 1, 0, 0 had better be 1, 1, and T of 0, 1, 0 had better be 0, 1, and T of 0, 0, 1 had better be minus 2, 3. Right? But having it written out this way makes it clear that this is just 1, 1, 0, 1, minus 2, minus 3 times the vector ABC. Right? So this shows you very clearly that this linear transformation really is just multiplication by this matrix, right? These columns that happen to show up here are exactly the same as the columns that show up there.